Hi, everybody. Welcome back to Pearson Plus. My name's Andy, and I'm going to be your guide today through some biochemistry questions. And I think we should just jump right in. When we are talking about biochemistry, you're talking about doing calculations in science, whether it be in biology, chemistry, physics, anywhere where we've got a mathematical relationship, we've got a scenario, we need to sort of figure out what's going on in the scenario and how to best apply the mathematical concept. There's a series of steps we can go through. And if you watch my videos before, you'll know I'm going to start with the reading of the problem and how to identify key components of the content. We're going to look at the concept and make sure we're clear on what the concept is. What does it mean when we're talking about this particular relationship, the Michaelis-Menten kinematics relationship? And then we're going to do math. So it's going to be sort of three phases. So let's start with the reading of the problem. So what I'm going to do is I'm going to share my screen with you here, and we're going to take a look at the actual question. So this is from the biochemistry section. Let's read it carefully. And as we read, I am going to use my highlighting tool to try and identify some key components of what's going on. Okay, so here we go. An enzyme catalyzes a reaction converting substrate into product at a velocity of 10 micromoles per minute when all enzyme active sites are occupied with substrate. So boom, right away, first sentence loaded with some vocabulary. It's got some data in it. I'm going to highlight this value simply because I think it might be helpful for us or useful for us as we move forward. Let's keep reading. Then I'll circle back and talk about some strategies here. The enzyme's Km, which is going to be a constant for this substrate, is 10 micromoles. Okay. Assuming that Michaelis-Menten kinetics are followed. So when you see something like this, you want to start thinking about, okay, am I familiar with that? Is that something I remember? Is this something I need to go look up? What is this Michaelis-Menten kinetics? What does that mean? Calculate the initial reaction velocity. So right away, it's telling us what we're going to need to find. We're going to need to calculate the initial reaction velocity, which is V naught. That's what we're going to be looking for. Oh, I missed my highlighting tool there. Hang on just a second. Let's do this. Oh boy. Sorry about that. We'll get this straight sooner or later. There we go. Look at that. All good. When the concentration of the substrate, that's what these little brackets mean. Whenever you see the brackets, it's a reference to concentration, and the S is going to be for our substrate, is 10 to the minus 2 moles. Show all of your work formulas, calculations, and explain what key concepts are necessary to solve the problem. So right away, it's a lot to take on. Okay. So as you're reading a scenario like this, my first step is I go through and I try to identify the data, which might be helpful for our calculations as we move forward to try and determine this initial reaction velocity. Once I've kind of gone through and I've read it once and I've highlighted those key components, I then go back and look and I say, all right, what are we talking about here? So an enzyme catalyzes a reaction converting substrate into product using this kinetics relationship. So what I am going to do is I'm going to switch over to my handwritten work, and we're going to walk through the concept a little bit. All right. So, and I think it's important that we do this. If you're familiar with the concept and you don't need to review what an enzyme is and what a catalyst is and how it works, feel free to skip ahead. But for those of us who need this support, let me kind of build this in as we go, because when you're doing these problems, there is the reading component, right? So reading comprehension, check. Can you read technical writing, find valuable information, and identify what the next steps are? Then there's a conceptual problem, right? Do you understand what's going on here? And then there's the math problem, and we're going to do the math part last. And that if you have the reading and you have the concept, sometimes the math falls into place a little bit easier. Okay, so here's a relationship. So substrates and products. So when we are talking about the role of an enzyme, I'm right here when I'm talking about enzymes. Oops, I'm right there when I'm talking about enzymes. Enzymes are these organic molecules. They're proteins, so your body's coded for them in your DNA. And the proteins that your body produces do everything from build eyeballs to elbows and everything in between. One of the things they do, those proteins, their job is to be an enzyme, which is to be a catalyst. And a catalyst, if I scoot my pen down just a little, a catalyst is something that promotes the completion of a reaction without actually participating in it. So a catalyst, the presence of a catalyst, allows reactions to happen easier. It allows reactions to happen at a more reasonable rate and a more reasonable temperature. Your body, to maintain homeostasis, has to have a cascading, a myriad, so many millions and millions of different reactions, from digestion to carrying oxygen to neural function to reproduction. The number of chemical reactions that have to happen and have to happen quickly is almost mind-boggling. Now, when you have the catalyst present, it allows those reactions to happen at a rate which allows your body to maintain homeostasis. It allows it to happen faster. And some of these reactions have to have an energy input to run to completion, to even initiate. And so what the presence of a catalyst does in any chemical reaction is to allow that energy to be less. And usually that energy comes in the form of heat. So our body has to sort of maintain homeostasis with temperature. So it can't have reactions that require 200, 300 degrees Fahrenheit. It's just not going to happen. So the body produces enzymes. They're proteins that act as catalysts so that this process, this chemical reaction, sometimes in physical chemistry, substrates would be referred to as reactants changing into products, reactants combined to yield products. Well, here we're going to talk about the term substrate. Substrate is the biomolecule the enzyme is going to act on to create the change that's going to yield products. Oh boy. So what that really means is that, and since we don't know in this particular problem what substrate, what product, what enzyme, we're just going to talk in generalities. What we do know is that the substrate is going to be changed, converted, modified to become a product, which the body needs. So that's what an enzyme does. So if we go back to the question says, assume that the Michaelis-Menten kinematics relationship holds. Well, here it is. And this is just something that we're going to have to know, is this mathematical relationship. Well, let's break down each individual component here. Okay, so V naught, when you ever see the low down there, zero down there, it's V, usually referred to that as V naught, is the actual rate of reaction. It's how fast this substrate is being converted into this product in the presence of the enzyme. Okay, so that's the actual rate of conversion. Vmax is the velocity or the rate of reaction maximum. If everything is firing on all cylinders, everything is maxed out, all substrates have plenty of enzyme, no extra enzyme, it's all matching up wonderfully and things are looking good. This is as fast as it could go in the best case scenario. Brackets around the S refer to the concentration of the substrate. Here it is again on the top and bottom. And then over here we have Km, which this is going to be our constant, okay, our kinematics constant. This is going to be a constants never change, okay, it's constant. So this is going to be something that is able to be true all the time for a particular enzyme and a particular substrate. Again, in this question, we don't really know what the actual enzyme and substrates are. However, we were given that constant, so I think we're going to be okay. So whenever you're doing these problems and you've got these components, you have to be able to substitute values for every single one of these except one. Otherwise, you're not going to be able to move forward. So in this case, we've got 1, 2, 3, 4, 5. We've got 5 different variables. Sorry, we've got 4 variables and a constant, don't we? And so we're going to be able to substitute. We've got to be able to substitute 4 of the 5 of those. So what I'm going to do is I'm going to scoot over here and I'm going to list them. Here's my V naught, my V max, my concentration of the substrate, and then my constant. Now, we read that question. I highlighted information. I'm going to go back to that highlighting. I'm going to go back to those values and I'm going to copy them over what I can fill in. Maybe I can get them all. Maybe I need to go back and reread and look for pieces of information I'm missing. Sometimes there's even assumptions being made in these questions where there's a constant that you need to know or a constant that you're expected to have memorized. So keep in mind, is there anything like that going on that maybe is not listed in the equation or in the question specifically, but might be able to be helpful, right? All right, so we've got our concept up here. We've got our mathematical relationship. We just need our values. So going back, right off the bat, this was our unknown. In the question, it said to calculate for the reaction rate. And I'm going to, let's see if I can jump back over there really quickly to get, not that way. Let's see if I can get back over there really quickly to make sure we remember what we were doing. Okay, here we are. So calculate, where my cursor is, calculate the initial reaction velocity, V naught. You see those action words, those thinking terms like calculate, show, evaluate. They're trying to tell you, hey, this is what we need you to determine in this scenario. Okay. And so right off the bat, that's where notice we have our concentration of substrate is here. Okay. We've got our constant is here. And then our max velocity is right here, because this was the velocity and it was described in that sentence when everything's firing on all cylinders and when all the enzyme sites are activated and occupied by a substrate. So that's where all the information is that we need and that I'm going to translate onto my handwritten work here, because I think it's a little bit easier to show the handwritten work when it comes to math. Okay, so Vmax. Vmax was listed as 10 micromoles per minute. Now, I'm going to pause here for a second because units are super important when we're doing these calculations. We're going to have to be certain that our units are going to line up to fit in here. I'm already thinking ahead. I've already seen a little bit of a problem that we're going to have to make sure we straighten out before we can substitute and solve. So the concentration of the substrate in this case was listed as 1 times 10 to the minus 2 molarity. All right, molar. And then the constant here was 10 micromoles in our units. We've got 4 out of the 5. What are we missing here? We've got our unknown. We've got our Vmax. We've got our concentration of our substrate, which we'll use not only here, but we'll also use here. So that's 2 of them. And then we've got our constant. Okay, this is where we're going to have to pause, because I know I get that way sometimes too when I miss it. I go, oh, I've got all my values. I'm good at algebra. I'm going to plop them in, plug and solve. I got this. And I miss a small piece. And this is the piece I'm going to point out right here. The Vmax is listed in micromoles per minute. And micro is a metric prefix like milli or centi, like millimeters and centimeters. Micro is 1/1,000,000th. It's 10 to the minus 6th. 10 to the minus 6th. Easy for you to say. And this one is also listed. The constant is listed in micromoles, but the concentration of the substrate is listed in its molarity. It's in just moles. So we're going to have to... We can't do it. You can't just take these numbers and substitute them into that equation and expect to get the correct value. It'd be like doing a problem with one car going miles per hour, one car going kilometers per hour, and you expect to get the same. You can't do that. You got to be measuring things the same way. And so we're going to have to do a quick conversion. And so I'm going to say that 1 times 10 to the negative 2 molarity is equal to 0.01 molar solution concentration. I hope we're okay with that, just going from scientific notation to decimal notation. All right. If not, there'll be another video we could probably reference you to help you with your scientific notation. But then I'm just going to go through a process of factor labeling, you might know it as, or you might hear it as dimensional analysis. We're just going to take that 0.01 molar and we're going to use what we know and we're going to convert it to micromoles. So I'm going to do that right down here. I'm going to scooch my paper up just a touch. Okay, so we know 0.01 molarity. That's our given. And I'm going to draw it here, and I'm just going to list it over 1. Any value we know, we can create a fraction out of it and put it over 1. It's not going to change that value. It's just a format. It's just a look that's going to be super convenient for us to convert the given to what we want. Now, if we know a relationship here that's going to connect moles to micromoles, we can use it here. So if I know a relationship between moles and micromoles, and if I know that 1 mole is equal to 10 to the 6th micromoles, I'm going to let that sit for a second and think about it. Is that okay? If these two values are equal, 1 mole is equal to 10 to the 6 micromoles. You could also say 1 micromole is 10 to the negative 6 moles. Either way, I chose this way because I think it's going to make the math a little easier. If these two values, top and bottom, are equal, then this fraction has a value of 1. I'm going to say that again. If the top and the bottom values of this fraction are equal, if we agree they're equal, any fraction with the top and the bottom, the numerator and the denominator equal, it's going to be a value of 1. And if we multiply anything we know times the value of 1, it doesn't change the outcome. It doesn't change the overall value. It might change the look. It might change the format. In this case, it's going to change the units. Because watch, if we have moles on top and moles on bottom, those are going to wind up canceling each other out. And the only unit now that we have left is micromoles. So then our process simply becomes 0.01 times 10 to the 6th over 1. Okay. 10 to the 6th, if we agree, can be a million. 0.01 times 1 million. Oop, just getting squished over there. Sorry about that. All right, so then we're going to wind up with a value of, we're going to move that decimal 2 to the left, bing, boom, and we're going to wind up with 10,000. Now, if the factor labeling 10,000, the only units we have left now are micromoles. All right, so if the factor labeling, that dimensional analysis, that process is new or still a little unclear, that's going to be something you're just going to have to practice, and we can keep working on that as well. But once you get that process down, although it's a little time consuming and can be a little wonky at times, you're like, I know what I need to do. I can solve this problem. I just don't have the units I need. This is a surefire way to get it. Okay. All right. So now what we know is that this is actually equal to 10,000 micromoles. So let me see if I have all my components. I know my marker's dying on me. Here we go. I know my concentration of the substrate. I know my constant. I know my Vmax, and I need to calculate my actual velocity in this reaction. Okay, so let me scooch it up. I'm going to scooch it up. Let's see if we can do it. I think we're ready. Isn't that crazy how much work goes into the preparation for the calculation? And I know as a student, I'm guilty. I know you want to, I know the equation. I want to pull the numbers, plop them in, and calculate it. And then I don't get it right. I get -1 here. I get nope, not correct. I get the wrong calculation. And if you're doing something, you're trying to make a calculation here for on a piece of paper for a test, you lose points. If you're trying to apply this to a real world situation, research could be ruined. Patient's medicine could be incorrect. So being sure that we know what's going on with these procedures in terms of paying attention to detail, doing that reading comprehension component, looking at the values, looking at the units, all before we do the calculation, just gives us a much better chance of being successful in the actual calculation. So I'm going to rewrite the formula. V naught equals, except I'm going to substitute. Instead of writing Vmax, I'm going to write what we know it is. And I'm going to write the units on there as well. I think that's important. And I'll show you why in a minute. All right, time, blah, 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 concentration of the substrate is, oh, we already converted that to 10,000. All right. So this point, all I am doing next is my constant, is I'm taking the values that I know to be true, and I'm carefully watching the formula, making sure I get multiply and addition where it's correct. And then, whew, okay, that looks a little scary at first glance, but I think we got this. We're going to go 10 micromoles per minute times 10,000 micromoles. Oof. Okay, watch this. So that is going to be 100,000. Watch this. Micromoles squared per minute. Right away, you're like, what? It just happened. Well, take a look. It's okay. Micromoles times micromoles, because you still have to account for all of the units. Micromoles times micromoles. There's two of them. Micromoles squared. Minutes are still there, so I got to do the minutes. Trust me, all that work we did ahead of time to make sure the units were correct are going to pay off now. A little bit of a payoff. It's all going to fall into place. Have a little faith. We're almost home. Divided by, now this is just an addition problem, so it's kind of funky. 10,000 micromoles plus 10 is 10,010 micromoles. Now we're going to do some division. We're going to go 100,000 micromoles squared divided per minute divided by 10,010 micromoles. Well, that's a mouthful. Okay, what we're going to do is realize that this will cancel one of those when we do our division. Okay, so I'm getting squeezed in here in the corner of my paper, but we're going to make this work. So as you do the calculations, and I've already done them ahead of time so that it could save us a little bit of time, you go and you take your calculator, 100,000 divided by 10,010 equals, and you're going to get a number that looks like this. 9.9900999. Well, that doesn't look super helpful, but it might be. And of course, our unit's going to be micromoles per minute. Okay. Well, that's pretty good. Isn't this, when you get an answer that looks like this, I hope it's starting to raise a red flag. Like, wow, look at all those decimals. I mean, is that really, just pause and ask yourself, can I really report an answer out to that level of degree of certainty? What this answer is telling me is I can go 1, 2, 3, 4, 5, 6, 7 decimal places over to the 10 millionth spot with certainty. Ooh, I don't know. The numbers they gave me in my in my values for my relationship, they gave me 10. They gave me 1 times 10 to the negative 2. They gave me 10. These values all show essentially one significant digit, one significant value. If this number was 10.00000, oh, that's telling me it was measured very precisely, not just 10.000. Okay, but it's not. These are not giving me that degree of certainty. So when I see an answer like this, I have to ask myself, can I be this certain? And in this scenario, the answer is no, you can't be that certain. We have not measured our values to that degree of certainty. So if you look at this number and you want to look at significant digits, one significant digit is 9. So 9 is our one significant digit that we can report. However, we have to look at the next digit to figure out if we need to round up or down. And so since it's 9.99999, I'm just gonna look at 9.9 and say, oh, I have to round that up to 10 as my significant digits. So a much more say accurate answer would be 10 for this question is going to be 10 micromoles per minute is going to be your velocity. So it's kind of wound up being the numbers on this scenario kind of wound up being a little tricky. We were so close to the maximum rate that when we looked at significant digits, we were almost at the max. We were very close to the maximum value. And there you have it. So when we look back, we do our reading, we review our concept, we find values, substitute, and solve. There was a lot of layers in this question. There's a lot of layers to sort through to get to the final answer. There are shortcuts. I'm going to recommend you don't take the shortcuts. Every once in a while, a shortcut will pay off and you'll still get the correct answer. But to increase the level of certainty that you're going to have in yourself as a learner is taking the time to read, identify important data, double check your concept understanding, then look for the mathematical relationship, substitute, check your units, substitute, and solve. Well, I certainly hope that the walking through this together was helpful, and hopefully that some of the things that we talked about are going to help translate to the next problem you do. Yes, answering this question is important, but give a man a fish versus teach a man to fish. Hopefully I'm helping you to learn how to fish so that way you're off and running on your own for the next one. Thanks for joining me on Pearson Plus. Have a great time. Science rules.